So we work on a wide range of things, and I'll give you a quick example of each one before I do one in more detail. So things that improve efficiency. So obviously improving the efficiency of vehicles and of industrial plant is a significant contributor to reducing our carbon footprint. Optimal operations, getting the very most out of the stuff that you own and making sure it lasts its full life. Enabling e-mobility, what role do fluids have in enabling that? Sustainable supply chain, so do we blend products using low amounts of energy? Do we actually blend low energy with neutral carbon footprint together? We aspire to that. And then the one that I'll turn to in the end to give you some examples is what we call impactful demonstrations. So just to explain the gist of it, area on that plot represents energy usage within a car. And as I've drawn the graphic there, the green bits are the amount of energy that's required to propel the vehicle. But the bit below the line are the amounts of energy that are being consumed to overcome friction within the engine, the gearbox, and the axle. And roughly said, on the legislative cycles, about 20% of a vehicle's total energy use is there to overcome friction. So I'm not suggesting you can remove all of that 20%, but you can remove some of it, and that something is material to the vehicle's overall fuel economy. And that's the focus of a lot of the work we're doing to enable efficiency. The next bit I've called optimal operations, and that's pointing to quite a lot of work that we're doing at the moment about putting sensors in lubricants and developing oil algorithms to sense how a vehicle or a piece of industrial kit is operating, and to make sense of all of that and to predict better the life of an oil and to have adaptive oil change intervals that reflect the duty that the engine's gone through and to change the oil at the appropriate time. Again, as we heard yesterday, electrification is an important change, particularly in the automotive sector, but increasingly so in the heavy-duty sector as well. And with that comes all sorts of challenges. You've got electrical windings, which are coated in varnish. You've got batteries to charge, ideally very quickly. You've got batteries to discharge as they're in use, again, probably with high current flow. And there's a need to cool those and to have avoid incompatibility between the lubricant and the electrical components. So all of that gives you a flavour of the range of things that we're involved with. What I'm going to do now is to give you a leading example of the work we've done. I've got two things there, the sort of bookends at silly extremes. So we've got a tiny car, which we developed from 2012 through to 2015. That was profiled at the Beijing Motor Show in 2016, I think. But the one I'm going to talk about most is about the Starship truck, a full-size Class 8 American truck that we developed from about 2014 until last year. Well, the mission with the truck was to make a truck which is exceptionally energy efficient. That's using all of the things that are spoken about so far. Using technologies that are available today so that we can reduce energy usage in a material way. So this is America today. So roughly said, there are 2 million heavy-duty trucks in the United States. Typically, they are loaded to 11.25 tons of cargo. Full capacity would be closer to 20 tons. They have an average fuel consumption or economy of 6.4 miles per US gallon, not imperial gallon. And if you work out the freight ton efficiency metric for that, that's 72 ton miles per gallon. By contrast, the Starship, as I said, was loaded to almost 20 tons. And despite the fact it was loaded to that level, it achieved almost 9 miles per gallon. So that figure's gone up considerably. Despite that, the economy has improved to there because of all the technologies that were involved. And you multiply these two together, and you get 178 ton miles per gallon. That's almost 2.5 times better. And remember, you can do that today with those technologies.